In the last class, we were looking at what do we mean by the transpose of a linear transformation. So we know what is the transpose of a matrix, and since every matrix corresponds to a linear transformation, so what we mean by transpose of a linear transformation and some properties we saw in the last class. So from this class, we'll be looking at what do we mean by eigenvectors or eigenvalues of a linear transformation. So I hope that you all are aware of the eigenvalues and eigenvectors of a matrix. So if you have n cross n matrix A, so you know how to find the eigenvalues, right? You find the characteristic equation A minus lambda determinant, and then you solve that polynomial to get the eigenvalues. But again, since every matrix corresponds to a linear transformation and every linear transformation corresponds to a matrix, so what do we mean by eigenvalues and eigenvectors in terms of linear transformation? So this is what we'll be looking at today. The last thing we proved was that column rank equals row rank. Okay. So from today we'll be looking at eigenvalues and eigenvectors. Okay, eigenvalues and eigenvectors. So first let me just define it, that let T is the linear operator on V. So what is a linear operator? Linear transformation we know, right? Linear transformation, it is a map from a vector space V to a vector space W. So whenever the domain and the codomain is same, that is whenever the map, the linear transformation is from V to V. Okay, in that case we give it a special name and we call it as linear operator. Okay, so let T from V to B be a linear operator. So linear operator is nothing but a linear transformation from the vector space V to itself. Okay. So we say that a non-zero vector V, or non-zero vector V of V, is an eigenvector of the linear transformation T if you have T of V is equals to lambda V for some scalar lambda that belongs to the field F. Okay. So what is a eigenvector? It is nothing but a vector which is non-zero. The first criteria is that it has to be non-zero, and then it has to satisfy this equation, that is T of V, the transformation of V is actually equals to some constant multiple of V. Okay, that is lambda of V, and this scalar lambda is actually called the eigenvalue corresponding to the vector or the eigenvector. So whenever we talk about an eigenvalue or an eigenvector, you please note that we will talk about eigenvalues in terms of eigenvectors and eigenvectors in terms of eigenvalues. So the point I am trying to make is that they both are always correlated. Okay, and they both are always studied together. They both always come together. Without knowing a eigenvector, we cannot find out what is the eigenvalue, or if we don't know what is the eigenvalue, then we cannot find the eigenvector. Okay, so they both always come together in a sense. So let us just see some examples. So we'll start with an easy example. Then let's say T is an operator from R2 to R2, and this T of xy is actually equals to 2x comma 3y. So now let me take two vectors, v1 which is 1 comma 0, that belongs to my R2, and v2 that is 0 comma 1, and this also is in R2. So now what is T of 1 comma 0? T of 1 comma 0 is actually 2 comma 0, which I can write as 2 times of 1 comma 0. So see, T of v, that is T of v1 is equals to some lambda 1 times v1, and here lambda 1 equals 2. So it means what? That 1 comma 0 is an eigenvector corresponding to the eigenvalue 2. Similarly, if you see that what is T of 0 comma 1, it is 0 comma 3, which I can write as 3 times of 0 comma 1. So T of v2 is actually equals to lambda 2 times v2, that is the eigenvector 0 comma 1, or 0 comma 1 is an eigenvector corresponding to the eigenvalue lambda 2 or lambda equals to 3. Okay, so the standard bases are actually the most basic example of the eigenvectors. So standard bases are always eigenvectors. Okay. Okay. Now let's see one more example. We call it example 2. That if my T is the identity map, okay, what happens then? Then any or every non-zero vector is an eigenvector with or corresponding to its eigenvalue 1. Because see, what we know, what is the identity map? Identity map is nothing but T of v is v. This I can actually write as T of v equals 1 times v, right? So here what is my lambda? Lambda is 1, and this is true for all v, okay, but since we only consider those vectors which are non-zero in nature, so we can say that every non-zero vector is actually an eigenvector corresponding to the eigenvalue 1 whenever T is my identity map. And why do we actually do not consider the zero vector? Because see, so why v is non-zero? Why do we consider v to be non-zero whenever we are talking about an eigenvector? So see, if I write that T of v is v times or lambda times v, okay. Now since v is 0, as v is 0, so T of 0 is what? Always 0, which is equals to lambda times 0, which is always 0, which is true for all lambda. What does it imply? It implies that whatever value lambda has, this equation is always satisfied, right? So this is a problem, because now we cannot say that okay, my 1 is an eigenvalue, because T of 0 equals to 1.0, it is fine, but then T of 0 is also equals to 2 of 0, 2.0, 3.0, or for that matter any lambda dot 0. So this is the case whenever my v is equals to 0, and that is why we consider only those vectors which are non-zero. That is, we consider the eigenvector to be non-zero. Okay, so this is fine. Now let's say one more example, that if my T is, let's say, an operator from V to V is not injective. Now what do we mean by not injective? it means that it is not 1 1. And if your linear transformation is not 1 1, what does it imply? It implies that its nullity has more than one element, that is, its nullity is a subspace obviously, and the nullity is more than just a 0 vector. So let my V belongs to this nullity of T, since T is not 1 1 or T is not injective, such that my V is non-zero. Then you see that T of V, which I can write as T of V, is what? 0. Since V is in the nullity of T, so it implies that T of V equals to 0. This I can write as 0 dot V. Now this is true for all V belongs to nullity of V. What does it imply? That every vector V that belongs to nullity of T is an eigenvector corresponding to lambda equals 0, because T of V equals to lambda times or 0 times V. So the thing to note here is that the eigen value is unique. So for an eigenvector, if I give you an eigenvector V, then the corresponding eigenvalue is always going to be unique. But if I give you an eigenvalue lambda, then the corresponding eigenvector need not be unique, right? So I can have more than one eigenvectors for an eigenvalue lambda, but for an so if I can have more than one eigenvectors for an eigenvalue lambda, but I cannot have more than one eigenvalues for any vector or for any eigenvector V. So this is something that one should keep in mind. So now let me just give one more definition of what do we mean by an eigenvector. Okay, so eigenvector, this was the eigenvector I talked about in terms of the linear transformation. Okay, so I'll just write the eigenvector in terms of matrix also, that let A be a n cross n matrix. So this is something that you already know, right? So we say a vector V is an eigenvector of A with eigenvalue lambda if V is an eigenvector of the linear transformation. Okay, so A is a matrix, and since every matrix corresponds to a linear transformation, so that linear transformation I am denoting it by L of A, that is linear transformation of A with eigenvalue lambda. So what does it imply? That any eigenvalue or eigenvector of the matrix is actually the eigenvalue or the eigenvector of the linear transformation or of the corresponding linear transformation. Okay. So for example, you know that in a diagonal matrix, the diagonal entries are the eigenvalues. Okay, so this is fine. So here I gave this just to like establish a relation between the eigenvalues of a linear transformation and the eigenvalue of the matrix. Because eigenvector of the matrix, I think you all are aware of, but since every matrix corresponds to a linear transformation, so they both are same actually, and that is what I wanted to emphasize here. Okay, so now let us see, or let us define what do we mean by an eigenspace. So we saw what is an eigenvalue, we saw what is an eigenvector. Now let's talk about eigenspace. Okay, so let T is an operator. Operator means a linear transformation from the vector space V to itself. Be a linear operator on V. Then the eigenspace of scalar lambda is the set of all vectors such that T of V equals to lambda of V. Okay, now what exactly does it mean? So I just emphasize on the point that given an eigenvalue, I can have more than one eigenvector. So for example, so this is just for the explaining part. Okay, explanation. So for the example that we just saw from R2 to R2, with my T of xy equals to 2x comma 3y, I saw that 2 was an eigenvalue and 1 comma 0 was an eigenvector. Okay, so I saw that T of 1 comma 0 was nothing but 2 of 1 comma 0. So 2 is an eigenvalue and 1 comma 0 is the eigenvector. Fine, but actually I can write this also, that T of 2 comma 0 is what? 4 comma 0. And this also I can write 2 times of 2 comma 0. It means corresponding to 2, 2 comma 0 is also an eigenvector. Similarly, 3 comma 0 is also an eigenvector. So what does it mean? It means that the eigenvector corresponding to an eigenvalue is not unique. Okay, and what we are doing here is that we are taking all possible eigenvectors corresponding to the eigenvalue lambda, and we are taking, or we are making, we are clubbing it to form a set. Okay, and that set is actually called the eigenspace. Okay, so okay, fine, I'll just erase it because this was just for your explanation. Okay, so T of V equals to lambda V. So now see that I have T V equals lambda V. And this actually I can also write T minus lambda I times V equals 0. That is, my V belongs to the nullity of the operator T minus lambda I. See, T is a linear transformation. T minus lambda is also a linear transformation, and this V, T minus lambda I of V equals 0. What does it mean? That V belongs to the nullity of T minus lambda I. So this is also this is an equivalent definition, or this is an equivalent relation between V and lambda. So either we can say that T of V equals to lambda V, or we can say that T minus lambda I of V equals 0. So hence the eigenspace of lambda is the null space T minus lambda I, which is a subspace of V. Now we know that the null space is actually a subspace of the vector space V, and now since the eigenspace is nothing but the null space of the operator T minus lambda I, And now since so the eigenspace is the null space of the operator t minus lambda I, and hence it is also a subspace of the vector space V, and that is why we call it as eigenspace. Okay, we call it as eigenspace because it is actually a vector subspace of the vector space V. And why it is a vector subspace? Because it is nothing but the null space of this transformation t minus lambda I, and we know that the null space is actually a subspace of the vector space. We are doing nothing much but just connecting the dots, whatever we have studied. We are just trying to connect the dots and come out with something meaningful. Okay. So now, okay, so I'll just write a proposition. Okay, proposition. Okay, so let T is an operator from V to V, be a linear operator on V. Okay, and let's say the dimension of V is my n, that is finite dimensional. So then if V1, V2, Vn is an ordered basis of V consisting of eigenvectors, then this T of beta is a diagonal matrix. Now what do we actually mean by this? So see, every linear transformation has a matrix. Okay, every linear transformation corresponds to a matrix. So what we have done here, we have taken a linear transformation on a finite dimensional vector space V. Okay, and we know that the matrix is actually depends heavily on the choice of basis we are keeping, because we know that linear transformation is defined, or it is governed by how it operates on the basis elements. Okay, or the matrix also is computed by looking at how the linear transformation is behaving with the basis elements. So we have a ordered basis here, v1, v2, vn. Okay, and if this ordered basis v1, v2, vn, if this consists of eigenvectors, so we saw that eigenvectors are also elements of V. So if this basis is nothing but a set of eigenvectors, okay, then the corresponding matrix that we will form, which I have defined or which I have denoted by T beta beta, is actually a diagonal matrix. Okay. So what what is the crux? The crux here is that we had a linear operator T, or we had a linear transformation T. We took a basis. The special thing about the basis was that it consisted of the eigenvectors. Okay, and if this happens, then we are claiming that the corresponding matrix will be actually a diagonal matrix. Actually, we can write conversely also, that if the matrix T, so this is just a notation. Okay, this is just a notation to represent the matrix corresponding to the linear transformation T with respect to the basis beta is a diagonal matrix corresponding to an ordered basis beta, then these VI's are eigenvectors. what is the full proposition here? That it works both ways. So if I have a basis of eigenvectors, then the corresponding matrix will be a diagonal matrix. And if I have a diagonal matrix, it means that the corresponding eigenvector or the corresponding basis must consist of the eigenvectors. So it works both ways. Let us just see the proof of this quickly. So let us prove the first part. Okay, that given beta v1 v2 vn is a basis of eigenvectors. So actually in this part actually we are going to use the concept of the concept that you studied in your 4th semester, that is the matrix corresponding to a linear transformation. Okay, so this is something that you studied in your 4th semester. So that concept is going to be used here to give a proof. So nevertheless, so okay, so this v1 v2 vn are eigenvectors. So if they are eigenvectors, so what does it mean? That by definition, that t of vj is equals to some lambda j vj, okay, where the lambda j is the eigenvalue of vj, because I said that eigenvector, we talk about them they come together. Okay, so we always talk about them together. So that is why by definition we can say that okay, t of vj is what? Some lambda j vj. And now actually if I so now here we are going to use the concept of the matrix corresponds to a linear transformation. So what we used to do to form a matrix of a linear transformation, we used to take the basis, basis elements, and we used to find okay what is t of that basis element, that is t of v1, t of v2, and here we are doing t of vj, and whatever we got we used to write it in a column form. So if we do it here, what we'll get? We'll get all the elements would be 0 except the jth row, that is here we'll get lambda j and then all will be 0. So this will be true for all j, right? So what is t of v1? T of v1 is nothing but the first element or the first row will have the element lambda 1 and the rest all will be 0. T of v2 is that first element is 0, I'm speaking column wise. So the first element is 0, second element is lambda 2, and then all zeros. So if we do it for like j equals to 1 to n, what we get? What type of matrix we will get? Obviously we'll get the diagonal matrix, and this is actually what we wanted to show, that t of beta is actually the diagonal matrix, lambda 1, lambda 2 to lambda n, where these lambda i's are the eigenvalues. So why are we actually interested in diagonal matrix? So the best thing about diagonal matrix is that it is very easy to find eigenvalues and eigenvectors of a diagonal matrix. And if you have a system of equation, that is, we have let's say 3 equations and 3 variables, and if you want to solve it, and if somehow the matrix representation, if you find that the matrix A is actually a diagonal matrix, then it is very easy to solve that system. And that is why we are interested so much in the diagonalizable process, or we are interested so much in the diagonal matrix. Okay, because it saves a lot of time. It is very handy in practical sense in solving the system of equations. Okay, so this is the proof of the first part. Now let us see the second part. That is the converse part. Okay, so let's say conversely. That let beta is a basis, okay, such that the matrix we get corresponding to beta is a diagonal matrix. That is, it is a diagonal matrix with diagonal elements as lambda 1, lambda 2, lambda n. Okay. So what does it mean? It means that T of Vj is nothing but lambda j Vj. Again, by definition, for j equals 1 to n, right? Because if it is a diagonal matrix, then how will you find T of x? T of x is nothing but we will multiply that element x or that vector x with the diagonal matrix, and whenever you do that, the multiplication happens in a column wise fashion. Okay, so this is something that I hope that you guys remember from your 4th sem classes, or like if you have understood, then I don't think there should be a problem. Okay, so yeah, so this T of Vj equals to lambda j Vj. Now, but what does it imply? What happens when what do we say when T of Vj equals lambda j Vj? We say that okay, if this happens, then actually my V1, V2 to Vn are the eigenvectors. Corresponding to the lambda j's. So this part actually maybe you can have a look at your previous notes or something. Okay, if you see that, you will get it easily. Okay. So now we actually go to an important concept. So let me define what do we mean by diagonalizable. That when we say that the linear transformation is diagonalizable, or when we say that the matrix corresponding to a linear transformation will be a diagonal matrix. They both are same thing. So a matrix, so if T is a linear transformation from V to V, and the corresponding matrix is a diagonal matrix, then we say that T is diagonalizable. Or if T is diagonalizable, then the corresponding matrix will be a diagonal matrix. So this is something that works both ways. So I'm just going to define it formally for you guys, but this is like the basic idea in it, that if it is diagonalizable, it means the corresponding matrix will be diagonal, and if the corresponding matrix is diagonal, it means that the corresponding linear transformation was diagonalizable. So we say a linear transformation or a linear operator for T from V to V is diagonalizable if there exists a basis beta such that my T beta V, that is the matrix corresponding to the linear transformation T with respect to the basis beta, is a diagonal matrix. Okay. And similarly, like this is one way, and other way we can say, so I'm just going to write it, that let A be an n cross n matrix. So we say A is diagonalizable if the linear transformation L of A is diagonalizable. Okay, so the first definition is actually in terms of the linear transformation, and the second we are actually saying in terms of the matrix. Okay, so they both are actually same thing, they represent the same thing. Only the thing is that the way of writing or the way of their depiction is different, but they imply the same thing. Okay. So we say that a matrix, any random matrix n cross n, we say that that matrix will be diagonalizable when the corresponding linear transformation is diagonalizable. Okay. So the important thing here is actually that uh, this is something that you must always remember, that every matrix corresponds to a linear transformation, and every linear transformation corresponds to a matrix. So this is actually a very important thing to notice here. Throughout this course, you will see whenever we study these kind of things, this is the basic idea on which all your proofs, all your statements are going to be based. Okay. So now I'll prove actually an important theorem for a proposition, whatever you can call it. So this is important, that if A is any n cross n matrix, then A is diagonalizable if and only if there exists a diagonal matrix D and a invertible matrix Q such that A can be written as QP Q inverse. So we say, or this is a very important theorem, okay, this is very important. So any matrix A is diagonalizable if and only if there exists two matrices, okay. First is a diagonal matrix 3 and another is a matrix, an invertible matrix Q, such that I can write A as a product of these two matrices, that is QD Q inverse. Okay, so this is very important. So I'll just prove this. Okay. So let my A is diagonalizable. So I'll prove both ways. So first I'm taking that, okay, let's say A is diagonalizable. Okay. And let beta dash have it here, that this v1 v2 vn be a basis of Rn such that the matrix corresponding to A, or the linear transformation corresponding to A with respect to the basis beta dash, is actually a diagonal matrix. So see, what we are doing is that since A is diagonalizable, it means that there is what does it mean? That the linear transformation, the linear transformation, or the matrix corresponding to the linear transformation of A with respect to the basis beta dash is actually a diagonal matrix. Okay. So now this L of A, which is the linear transformation of A, I can actually write it as I times LA times I. Okay. This is fine because I is the identity matrix, I can write it. So this identity matrix is actually in Rn, because everything we are talking about here is n-dimensional. Okay. And now let beta be the standard basis of Rn. So my matrix A and so the matrix A and the matrix which corresponds to L of A, that is the linear transformation, they both are same whenever we are talking in terms of the standard basis. So this is a result that we know. Okay, So this is a result that you must have read in your fourth semester part, that if you take the standard basis, then the matrix and the matrix corresponding to the linear transformation, they both are same. So that is what actually we are using. So what does it mean? It means that I times A times I with beta is actually equals to A. Okay. So now here actually we are going to use a property of change of basis. Okay, and this is something that again, this is something that you must have already studied in your fourth semester, but I don't know whether you guys remember it or not. But if you don't remember it, please go and have a look, because this is really important. So what does it say is that, let's say that I have a linear transformation T, and I make a matrix with respect to the basis beta. Okay, so I took the linear transformation, I took the basis beta, and with these two I can create a matrix, right? Similarly, if I take a different basis, I'll get a different matrix, because if in the first or second class I told you guys that the matrix and linear transformation is actually connected with the bridge. The basis actually works as a bridge between the linear transformation and the matrix, because if you change the basis, your matrix can change. Okay, so one basis is beta, one basis is beta dash. The same linear transformation, when works on beta or when works on beta dash, will give two different matrices. Okay, but there is a property that actually we can calculate what happens whenever we change our basis from beta to beta dash. Okay, so that property actually we'll be using here, and I want you guys to actually go and have a look if you guys don't remember it. So we can actually write it in like this. So I will be from beta to beta, and this is beta dash to beta, and then this I can write as beta to beta dash. So this is actually a property. Okay, and this property we are using here, and it was in your fourth semester syllabus. Please go and have a look if you don't remember it. So what I can do is that I can take just my q as the first component, that is I from beta to beta. Okay, and if you do that, it turns out that your q inverse is nothing but this beta to beta dash, because the inverse of identity is nothing but identity itself. So here what I can write A as q d q inverse. Okay, and this is actually what we wanted to show. So the first part is done, right? Because this is what we have to show, that there exists some matrix D and some matrix Q, such that I can write A as Q D Q inverse. Fine. Now let us see the converse part. The conversely, that let A has this form, that is A has this Q D Q inverse form, where D is the diagonal matrix and Q is invertible. Okay, so let beta be the standard basis. So what is my D of Ej? So diagonal matrix of Ej. Whenever you take a diagonal matrix and you multiply it by Ej, you get nothing but lambda j Ej, because your Ej's are the standard basis. Okay, where my D is actually a diagonal matrix, and the elements are lambda 1, lambda 2, lambda n. So that beta dash I am taking as QE1, Q into QEn. then what happens to my dq inverse times qej? What is this quantity? This quantity is nothing but just q times of, I can write it as lambda ej. And what is this? This is nothing but lambda times q ej. But beta dash, so what does it imply? So what does it imply? It implies that my q ej actually is an eigenvector, vector of q dq inverse. Okay, but we also know that my beta dash is a basis of Rn. And what does it imply? It implies that q dq inverse, hence we can say that my q dq inverse is a diagonal matrix with respect to beta dash. You see, it uses a lot of properties of your previous knowledge. So please go and have a look if you can't recall it properly, because you will be using it quite frequently. Okay. Yeah, so okay, so we said this result, what does it say? It says that okay, a matrix A is diagonalizable if and only if you can find some matrix D and some matrix Q such that A can be written as Q dQ inverse, where D is diagonal and Q is not immutable. Fine, this is the definition. But actually, how do you find this D and how do you find this Q? This remains a question. So if that D and Q exist, then it is diagonalizable, or if it is diagonalizable, then this Q and D will exist. That is fine. But then how are you actually going to calculate? This is still a question that needs to be answered. So for this, I will just write a proposition which I am not going to prove here, that let A be a 10% matrix and let this beta, it is v1, v2, vn, are vectors in Rn such that A of Vj equals to lambda j Vj. Okay, and beta is a lie. So basically, this v1, v2, vn are vectors that satisfy this condition. Okay, that A of Vj equals to lambda j Vj. So then my A is actually q dq inverse, which is fine. Okay, these Vj's are not zeros. Okay, Vj not zero. Yeah, so then A is diagonalizable, that is A is equals to q dq inverse. That is fine, we just saw. But how do you find this q and d? So this q is actually nothing but the eigenvectors itself, v1, v2, vn, and this d is nothing but the matrix consisting of elements lambda 1, lambda 2, lambda n, where these lambda i's are the eigenvalues J. Fine. Okay, so this is okay, and this is very easy to prove. I think you guys should try it. Okay, yeah, so fine for today. I'll just take the attendance now.